Okay, Allen High School kiddos, we've spent quite a bit of time talking about the effects of either partial pressures or molarities on the rate of a reaction. And now we're going to hit on the last couple of key ones. And then if you look in your notes, there's a chart at the end and vocabulary words at the end and a summary table at the end. So lots of things to help you study at the end of your notes. Now, let's take a look at temperature. Most of you know as you increase temperature, you're going to increase the rate of a reaction, right? You put your oven temperature up higher, you're going to cook your pizza a little bit faster. Now, I'm not sure if you remember from pre-AP, but temperature is the measure of average kinetic energy. And so we can get, if we graph energy of either the molecules or in this case of the collisions of the molecules, we get a Boltzmann distribution. So that's called a Boltzmann distribution. B-O-L-T-Z-M-A-N-N, because we need more dead guys in our conversations. So it's a Boltzmann distribution. Now, when we move from a lower temperature to a higher temperature, you should be able to explain in terms of collision theory. It's really what we're after in terms of collision theory, why our rate increases. So in IB, I want you to pay especially close attention to this because I've seen this on IB tests. They really want you, and I don't blame them, they want you to be able to analyze these graphs. Notice the differences here. The peak shifts. Not all collisions happen with the exact same energy. But as you go up in temperature, you notice that the peak shifts that way, left to right, okay? Now, the other thing I want you to note is that the peak height, so three key aspects of it, the peak height here goes down. Now, the area under the curve is the same. Now, that's not as easy to see, but the area under the curve is the same. But that peak height goes down a little bit. And then it trails off higher over on this end here. So this is where you get the real gain, is on that end there. So you should be able to describe those three effects of increasing the temperature. We increased it. T2 is greater than T1. So now, if we drew this line here, if we followed this line up, that represents the activation energy. So all molecules with collisions greater than that are going to be effective collisions, assuming correct orientation. You have to be very careful, assuming correct orientation. So what the graph is showing is that at the lower temperature, this fraction has enough energy to get up and over the activation energy of your potential energy curve, and assuming orientation would go on to make products. Now, when I increase the temperature, I get many, many more collisions that are effective. It's the whole area under the curve that represents our effective collisions. So temperature, by increasing the temperature, we increase the energy of the collision, and we increase the fraction of molecules that have enough energy, sufficient energy to make it up and over that activation energy curve. Now, mathematically, what we use for this is the Arrhenius equation. And, I'll get a pen here, that'd be better. Arrhenius. If I've lost you, I want you to take a look here. I'm on page 13. And the Arrhenius equation is where we get not only our temperature effect on the rate, but that's where we see our activation energy effect on our rate. And it's a wonderful little equation, except that it's an exponential equation. And you know, we chemists, we love a good straight line with an r squared close to 1. So if we rearrange this equation by taking the natural log of both sides, it is not something you would have to do. You would get this equation here. And then we could graph it, much like what we've graphed before. I'm not going to do an example of graphing, but boy, you better memorize what we're doing here, because this is a critical way of finding our activation energy. So if we plugged in the natural log of K, if we graphed that on the y-axis, and we graphed 1 over T on the x-axis, and we have to have Kelvin. Remember, Celsius does not make physical sense. It's got to be Kelvin temperature. Now, this A here is where we get really, in part, the orientation. It's called a frequency factor. And if you look in your book, if you're doing the book notes, you'll see that it includes a steric component. That's an orientation component. And so that frequency factor can be determined experimentally as well. So K really wraps in almost every effect other than concentration on the rate, every variable that affects the rate. So we've got ln of K versus 1 over T. If we graph that, we get a straight line, and our slope will be given as negative E sub A over R. So in our example over here, our slope is minus 1.2 times 10 to the 4th. And that's going to be equal to minus E sub A. And then I want you to note something here. Energy is in joules. That's our SI. We're going to see 3 equations that look very similar. And this slope term gives an energy, or in one case, a pressure term. But here's my point. That has joules. And so what you have to use is the R value here has to be the one for joules. And that's 8.314. So if I just toss that in there, my 8.314, I would have my activation energy in joules. So we're going to move on to catalysis. We briefly mentioned a catalyst at the beginning when we're talking about potential energy curves and mechanisms. I want to tie this all together. This will kind of bring our conversation back around to completion. A catalyst provides an alternative pathway. And that's critical. When you're doing your justification, it's not enough to say that a catalyst speeds up a reaction. You have to say why. Telling us that it speeds up the reaction, that's a pre-AP level question. I want you to know why. And there's 2 ways. So that's a key point. It's an alternative pathway. And that pathway is going to have a lower activation energy than original. So more molecules have enough energy to get up and over the activation energy curve. It can do this by either stabilizing the activated complex, or it can form a new activated complex. Either one. So remember that activated complex, if we had a potential energy curve, we get a little bit better color for this. If you look at your potential energy, we'd have R and P, and up and over. Up at the peak, that was where our activated complex was, also called a transition state. Now, it speeds up the reaction without being consumed. We saw that when we did mechanisms. It was there at the beginning and it returned at the end, so we don't have a net loss. And you've seen this before, not only in the context of chemistry, but biological catalysts called enzymes are actually some of our most effective catalysts known to humanity. So, our bodies, biology has developed in a way that is so beautiful and so wonderfully efficient. Okay. Now, this shows you the diagrams that we've seen before. All right. So this was our activated complex in the uncatalyzed, and it now has a lower energy because we've provided an alternative pathway that stabilizes the complex or provides a new complex with lower energy. But the key here is we have a lower activation energy. And it's interesting to note, I want you to pay attention to this aspect of it as well. Do you note that we've also decreased our activation energy in the reverse direction. So a catalyst does both. It decreases it in the forward and the reverse. So that's critical. We'll see that in the next unit, that E sub A forward is reduced and E sub A reverse. So it doesn't have an effect just on the forward direction. It has one on the reverse direction too, assuming it's reversible. Now here we have that curve. Remember, this is the Boltzmann distribution for a given temperature. These are the same graphs, the same temperature, and you notice the area over the curve here that have enough energy to get up and over the activation energy curve. In this case, if I kind of extended this line up so you could get a sense of what they would look like overlaid on top of one another, you would see that a much greater fraction have enough energy to get up and over the lower hill. Okay? And I think that's logical. If you were going to ride bikes, if you were in a marathon, and you're just going to naturally have some people that can make it over the big hill and some people that can't. But more people will make it over the little hill than can make it over the big hill. All right, that's it. There is in your notes a variety of helpful tools you want to take a look at. There will be some AP questions. I'll be doing some videos on some AP questions, and that will also help you for your test, and we'll be working on homework in class. So until then, this is signing off.